We now start the second chapter, second module. So, the second chapter is on vector spaces, and in the second module we will be talking about subspaces followed by examples, some natural examples of subspaces of Rn and Cn in particular, and then we will introduce the notion of linear combination of vectors in a vector space, and we will see that the concept of linear combination of vectors is again trying to formalize and generalize the notion of solvability of a system of linear equations. Let us now introduce the concept of a subspace of a vector space. Suppose that V is a vector space over a field F and W is a non-empty subset of V. We say that W is a subspace of V if W itself is a vector space over F under the operation of V restricted to W. What does that mean? Recall that V itself is an abelian group with respect to the binary operation plus. So, that means plus is a binary operation which is a map from V cross V to V. Now, when we say that W itself is a vector space over F under the operation of V restricted to W, that means if we restrict that binary operation plus to the subset W cross W, then the image of that map is going to be in W. In other words, if we take x and y from W, then x plus y will be in W. Moreover, V has a scalar multiplication with respect to F. That means there is a map from F cross V to V. Once again, if we restrict this map to the subset F cross W, then again the image is going to lie in W. That means if we take a scalar lambda in F and a vector x in W, then lambda dot x is going to be in W. What we have said just now is precisely the next theorem. So, W is a subspace of V if and only if given x y in W and lambda in F, x plus y belongs to W and lambda x belongs to W. So, a standard way of writing these things, or a usual way of calling these things, would be W is closed under addition and scalar multiplication. Well, proving this is easy, and it exactly follows from the definition, from that particular portion of the definition which says that W itself is a vector space over F under the operation of V restricted to W. Let us see a couple of very important examples. Recall that we had defined the vector space F raised to x, where F is a field and x is a non-empty set. F raised to x was defined to be the collection of all functions from x to F, and that was a vector space under pointwise addition and scalar multiplication of functions. Let us now look at the subset consisting of those functions from x to F which vanish at a fixed point A. That means the collection of all F from x to F such that F of A is 0. This is surely a subset of F to the power x. Not just that, this is also a subspace. How do we prove that? First thing we have to show is that V is non-empty, that means there is at least one function which vanishes at A. Well, we can take the 0 function, that means the function which is 0 for every element in X, and therefore V is non-empty. Now we can invoke the previous theorem to prove that V is a subspace of f to the power x. That means that given f and g in V, we have to show that f plus g belongs to V. How was f plus g defined? F plus g of x is equal to fx plus gx. Therefore, if fa and ga are both 0, then f plus g of a would be fa plus ga, and that would be 0 plus 0 equal to 0, 0 in the field f. Therefore, f plus g belongs to V if f and g both belong to V. Now, if lambda belongs to f and f belongs to V, then lambda f at A would be lambda times f of A, that is lambda dot 0, that is equal to 0 in the field f. Therefore, the pointwise addition and multiplication, that means the scalar multiplication of functions, actually makes V a subspace of f to the power x. So, a very important example for a subspace of the big vector space f to the power x, and that is given by V. Now, one more. Recall that Rnx was defined to be the collection of all polynomials with real coefficients whose degree is at most n, and Rx is nothing but the collection of all polynomials with real coefficients. So, Rx surely contains Rnx. Now, what is important here is that Rnx is not merely a subset of Rx, it is also a subspace, which means that if you have two polynomials f and g coming from Rnx, then f plus g is also going to sit in Rnx. That means the degree of f plus g is also at most n. Similarly, if I have a lambda in R and f in Rnx, then lambda f is also a polynomial whose degree is at most n. Two more very important, very classical examples. So, R01 denotes the set of all Riemann integrable functions on the closed and bounded interval 0, 1. Now, again from basic calculus knowledge, we know that if there are two Riemann integrable functions f and g on the closed interval 0, 1, then f plus g and also lambda f, where lambda is a real number, are Riemann integrable on the interval 0, 1. So, R01 is again a very natural example of a vector space over R, and C01, which was defined as the collection of all continuous real valued functions on the closed and bounded interval 0, 1. And again, we know that every continuous function on 0, 1, for that matter on any closed and bounded interval a b, is Riemann integrable. So, C01 is indeed a subset of R01. C01 and R01 are both vector spaces, and the operations are nothing but pointwise addition and scalar multiplication of functions. So, C01 is indeed a subspace of R01. Next example.
Sir, next example থেকে ধরুন সাইলেন্স। নেক্সট এক্সাম্পল থেকে যাচ্ছে রোল।
The next example is about C infinity 0 1, which stands for the collection of all real valued C infinity functions on 0 1, that is the collection of all infinitely differentiable functions on the interval 0 1, the functions are real valued. Again, with respect to pointwise addition and scalar multiplication of functions, C 0 1 is a vector space over R, and we know that every differentiable function is continuous. Therefore, C infinity 0 1 is a subset of C 0 1, and again the operations being nothing but the pointwise addition and scalar multiplication of functions, C infinity 0 1 is in fact a subset of C 0 1. So, if we see these two examples together, then we see that we have created a tower of vector spaces which is C infinity 0 1 contained in C 0 1 contained in R 0 1. Now, we see a very natural subspace of Rn, namely the set S, which is the collection of all n tuples alpha 1 to alpha n, such that A dot alpha 1 alpha 2 alpha n is 0, I mean the 0 matrix. You know what this is. This is nothing but the collection of all solutions of the homogeneous system of equations A x equal to 0. Now, we claim that S is a subspace of Rn. How? First of all, S is non-empty because the 0 solution or the trivial solution is in S. If there are two such alpha 1 to alpha n and beta 1 to beta n in S, then alpha 1 plus beta 1 etcetera alpha n plus beta n and alpha 1 minus beta 1 etcetera alpha n minus beta n, these two n tuples are also in S. This is easy to see, and if alpha 1 to alpha n is a solution and lambda is a real number, then the scalar multiple lambda alpha 1 and so on up to lambda alpha n is also a solution. So, these three bullets actually show you that S is indeed a subspace of Rn. Now, let us try to classify the subspaces of Rn. So, to begin with, let us try to understand the subspaces of R and R2 first. So, the theorem says a subspace W of the vector space R is either just singleton 0 or R itself. The second part of the statement says that a subspace W of the vector space R2 is of the form W is equal to S A1 A2 plus T B1 B2, where A1 A2 and B1 B2 are fixed elements in R2 and S and T vary over the set of real numbers. So, it shows that if A1 A2 B1 B2 both happen to be 0 vector, that means the tuple 0 comma 0, then W is nothing but the singleton 0 comma 0. On the other hand, if A1 A2 is 1 0 and B1 B2 is 0 1, then W is nothing but the whole of R2. Therefore, there is an indication that the singleton 0 0 and R2 can be seen as subspaces of R2, but the question is, do we have subspaces other than singleton 0 0 and R2? Let us prove this statement first. Let us prove the first part of the statement. that is every subspace of R is either singleton 0 or R. So, suppose W is a subspace which is not the singleton 0. That means there is at least one x in W such that x is not 0. Therefore, 1 by x exists as a real number, and we can write any real number y as y dot 1 by x dot x. This shows that y belongs to W because W is a subspace and x belongs to W. Therefore, every scalar multiple of x would belong to W. But y was chosen arbitrarily, and therefore, W has to be the whole of R. Now, the second part of the statement, let us try to classify the subspaces of R2. Suppose that W is not singleton 0 comma 0 and W is a subspace of R2. That means that there is at least one A1 comma A2, a tuple in W which is other than the 0 tuple. Let us take W1 to be all the scalar multiples of A1 comma A2. You know what that geometrically means. It is nothing but the line passing through the point 0 comma 0 and the point A1 comma A2. Since A1 comma A2 is in W and W is a subspace, therefore, W1 is contained in W. If W is equal to W1, then we are done. Otherwise, there would exist an element B1 comma B2 which is in W but not in W1, and now we show that W is of this form, that is S A1 A2 plus T B1 B2, where S and T belong to R. Let alpha beta belong to W. We show that there exist real numbers S and T such that SA1 plus TB1 is equal to alpha and SA2 plus TB2 is equal to beta. This should show that W is contained in that set which we wrote in the previous slide. Now, if we solve these two simultaneous linear equations, then we can see that choosing S to be alpha beta 2 minus beta B1 by A1 B2 minus A2 B1 and T to be alpha A2 minus beta A1 by A2 B1 minus A1 B2 serve our purpose. The only thing we have to be careful about is the denominator, which is A1 B2 minus A2 B1, but that is not 0 because A1 A2 and B1 B2 are non-collinear. If I show you the previous slide, A1 A2 and B1 B2 are not collinear because B1 B2 belongs to W and it avoids W1. And what was W1? W1 was the line passing through 0 0 and A1 A2. So, if B1 B2 is not in W1, that means B1 B2 is not sitting on the same straight line passing through the origin and A1 A2. And therefore, A1 B2 minus A2 B1 cannot be 0. So, we have solved this simultaneous equation for this choice of S and T, and therefore, we have proved that alpha beta, which was in W, actually belongs to this set S A1 V2 plus T B1 B2, where S and T belongs to R. After definition and examples of subspaces, we now ask a pertinent question. We have seen that the set of solutions of a system of homogeneous equations is a subspace in Rn. Now, suppose we ask, what about the converse? That is, suppose we start with a subspace W of Rn. Can this subspace be seen as the set of solutions of a system of homogeneous equations? We will see that the answer is yes, but we have to wait. We have to introduce some more concepts before we formally establish this fact. Let us now introduce the concept of linear combination of vectors in a vector space V over a field F. In order to see systems of linear equations from a more general setup, from a more general point of view. We can ask these questions. The homogeneous system of linear equations is a subspace of Rn or Cn. Is the converse true? That means, if we take a subspace of Rn or Cn, can that be seen as the set of solutions of a suitable homogeneous system of linear equations? And the second question is that we have just now seen that R2 as a vector space has subspaces which are of this form. In fact, any subspace can be written in this form for suitable A1, A2 and B1, B2. Can we see that this is the set of solutions of a homogeneous system of linear equations? We now introduce the notion of linear combination of vectors. Let V be a vector space over a field F and S a non-empty subset of V. A vector small v in the vector space V is said to be a linear combination of vectors of S if V can be written as A1 V1 plus A2 V2 dot 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 An Vn for some vectors V1 V2 Vn in S and A1 A2 An in the field F, and these A1 V1, A2 V2 and An Vn, these are of course the scalar multiples of the vectors V1 V2 Vn with respect to the scalars A1 A2 An. Let us see some simple examples of linear combination. If V is the vector space R2 over the field of real numbers, then the vector 2, 3 can be written as a linear combination of 1, 0 and 0, 1. And in the next example, we see that the same vector 2, 3 can also be written as a linear combination of 1, 0 and 1, 1. The scalars change accordingly. Now, in the third example, we show that very vector 2, 3 can no longer be written as a linear combination of 1, 1 and 2, 2. Well, the explanation is clear. If we can write 2, 3 as a linear combination of 1, 1 and 2, 2, that means 2, 3 is a dot 1, 1 plus b dot 2, 2, which would lead to a plus 2b is equal to 2 and a plus 2b equal to 3, which is of course absurd. Therefore, it surely depends what are the vectors in the set S which we use for writing the linear combination. And here geometrically it is easier to understand that 1, 1 and 2, 2 are actually sitting on the same straight line passing through the origin and the point 1, 1, and the vector 2, 3 surely does not lie on that line, and therefore, it is quite natural that 2, 3 cannot be written as a linear combination of V1 and V2 in this case. This theorem is going to show you the connection between linear combination of vectors and system of linear equations. So, let V be the vector space Rm over the field R. Let V1, V2, Vn be n vectors in Rm. Let us write these vectors V1, V2, Vn as column matrices, and let us form the matrix A with these vectors V1, V2, Vn as columns. Therefore, there will be m rows and n columns. Now, the statement is that a vector V in Rm is a linear combination of V1, V2, Vn over R if and only if there is a solution to the system of linear equations A dot x is equal to V. Well, it is easy to see if we just rewrite A dot x. So, a solution exists to the system of equations A dot x is equal to V if and only if there are real numbers x1, x2, xn such that A dot x is equal to V, where x is nothing but this column matrix x1, x2, xn. But A dot x is nothing but x1 v1 plus x2 v2 and so on xn vn. Therefore, a solution exists if and only if V can be written as x1 v1 plus x2 v2 and so on up to xn vn. That means, V is a linear combination of v1 v2 vn over R. This brings us to the end of the second module of chapter 2 on vector spaces. We have learned so far the definition of a vector space over an arbitrary field, subspaces. We have seen examples of subspaces. We have also learned what is meant by linear combination of vectors in a vector space. And the most important thing is that we have seen the connection between linear combination of vectors and systems of linear equations. And we have asked a very important question, that a subspace of Rn or Cn or in general Fn, whether it can be seen as the set of solutions of a system of homogeneous linear equations.